them were right, because these clouds came in around 7, and they never went away. They just kind of stayed there. There were a couple little sucker holes, but they were so small that it wasn't even worth chasing them. So Tracy and I kind of packed it up early.
And, we were on the observing the amateur field and set up, and then I just like look over to the east, I guess it is, and also it's like, wait, what's going on? Like, there's not supposed to be clouds. And I'm like, oh, I'm sure they'll just pass. And I look at the forecast, like, oh yeah, they'll just pass. By 10 o'clock, we're like, never mind, we'll just go back to the camper.
Yeah, exactly. Yeah, so we stayed the extra day, thinking we'd get some nice observing on Tuesday night, but we wound up getting skunked that night. But it was still nice. It was a nice time to be up there. And Tracy's working on her Messier list, so she's about halfway through it, and I've been working on the Astronomical League globular cluster list. So I'm making good progress on that. And it's just, you get so spoiled up there because the stuff is just so easy to find on a good night. That it's really the way observing should be. It just shouldn't be like you're just struggling everywhere to get some kind of contrast, but it is the way it is.
Yeah, I'm always amazed that around here in King of Prussia, looking for M4 is very difficult. And at Cherry Springs, it's a binocular object.
Yeah.
You can't see it here with an 8-inch dot, and then go to Cherry Springs and you can see it with a pair of binoculars.
Yeah.
It always
there's so much that's even naked eye up there. You just look up and okay, there it is. Yeah. But I think sorry, Lou.
I was just labeling the point how confusing Cherry Springs can be with all the stars up there. It's like, where's Walter?
It is.
I got confused.
Tracy got the one time she got confused too. It was later in the night, and she said, I don't know what I'm doing wrong. She said, but I can't find anything anymore. And she was getting frustrated, so I walk over and her eyepiece had fogged. I said, I said, maybe we should put the dew heater on maybe we should have put the dew heater on your eyepiece a little earlier. Sorry, babe.
Yeah, I was saying it was the first time it's been that dark. I got confused finding Polaris actually, because also there's stars around it. Here at home, it's like you see Polaris and a couple more. Up there, it's like, wait, which one is the Polaris again?
Yeah, I know.
Definitely a lot more stars. So.
Yeah, one of the things that threw me off years ago. I've been going up there for 20, I guess, 22 years now, and it was probably like 4 years into it or so, and I was working on the Messier list, and I would be star hopping, and there you can find relatively faint stars that are close to the object, much closer than you can if you're not in a good site like that. So you don't have to star hop as far. And I found that, like, I was looking up and I would see the star, the faint one that I was, going to use as my target to start from. And then all of a sudden I'd look up again, I would keep looking and it would be gone and I couldn't find it. And I kept doing this. And it took me probably like till the next year to realize that the Milky Way, the light from the Milky Way up there was actually messing with my dark adaptation and causing those faint stars to fade away if you looked up too long.
Yeah, Lou and I talked about that.
Yeah, then
First time Lou and I went out there, we were like, "What's this fluorescent overhead light?"
Right.
Yeah, we were upset. We were ready to wring someone's neck. Turn that light off. It's the Milky Way.
Oh, it's the Milky Way.
Wait a minute, it's the Milky Way. So I would wind up having to look down at the ground for a while whenever I was trying to find the faint stars, so that my vision didn't get washed out from the Milky Way. It's a good problem to have.
Yes.
We're going to get started. A number of us are, a number of the regular reports are out. So we're going to be able to crystallize a lot of those reports into what I present for you relatively quickly. This is a view of the.
Oh, sorry, Harold. I muted you by
Yeah, you
mistake.
missed. You missed. It's okay. I clicked the wrong place. Okay, this is a view from the Overlook Trail, looking north on the Susquehannock River. Actually, Peach Bottom Nuclear Plant isn't far from there, and you can see a bridge over the Susquehannock River in the distance.
I've gone water skiing in that water.
It's very shallow. You don't have to worry about falling in. You could probably stand anywhere. Anyway, that's Susquehannock State Park. It's only about 90 minutes away, and we just Jeremy and I were at last weekend. We were at the Star Party. It's going to be repeated on October 6th, the 6th through the 11th. There is a website there, yorkcountystarparty.org. There's also a group. It's the same Groups.io host as we used for our listserv. And Phil this is the email Phil's using. Phil used to be with an astronomy club. He seems to be rather proud of the fact that he has nothing to do with an astronomy club now. This is his sole, this is his reason d'etre or whatever. And he's very excited about this. He's actually talked to people about next year's York County Star Party at the park. He's hooked up with a nature person there who has agreed that they will turn all the lights red where need be, instead of him using Elmo wrapping paper around some of the lights and black plastic bags over other of the lights to eliminate the white light in the area. The ball field where we camp is flat, unlike Blue Mountain. It's dry. It's trees all the way around, but there's also a light dome all the way around that the trees mostly conceal. It's a pretty good sky. It's comparable to Blue Mountain, as Jeremy said. And I had 3 good nights there. I was supposed to go out Wednesday. Wednesday, all those storms blew through, and I decided I didn't want to be in a tent in an electrical storm. I'm funny that way. So I went out Thursday. But Thursday night, Friday night, Saturday night, really good viewing, real good experience. Jeremy and I saw a transit of Io and missed by 24 hours something hitting Jupiter, because apparently Jupiter was smacked into the following night. Isn't that right, Jeremy?
Yep.
Yeah. So this is the information. Don was also there, and Don's going to speak to us briefly about mural program. Don was out there, and there were some officers from Chesmont also out there. We had a good crowd. And this is a photograph of the Bubble Nebula field that was taken by, and I'd have to switch over to my other screen, taken by somebody who was at the Star Party. There were a number of astrophotographers there. One was set up right next to me. And they were just setting up, and they got some pretty good photos out of the evening. Anyway, we have a lot of new members since July. So welcome to, if you're one of the new members and you're on, and I didn't see anybody in there, raise your hand or something, but greetings. We are at magical, I think we're pretty close to 200. I'll let Lewis give us the exact number, but we're huge. We're a very large club now, and that's great. That's very exciting.
A whopping 202.
202. That's fabulous.
Crazy?
Yeah, that's crazy. So welcome all these members who've joined us since July 26th. Remember, our last live meeting was July 24th at Fort Washington. And now, so that's Brian Lee's report, and now is Janet Rush's report. There are 2 upcoming outreach events. One is at Brooke Elementary School on October 1st. Actually, both of these are on October 1st. They're looking for telescope setup, and please reach out to Al Lamparty if you can help out with that. And the other one is also October 1st. That's at the Briar Bush Nature Center in Abington. And you can contact Janet directly. She's at outreach@dvaa.org, and so forth. So it's close to New Moon. You can do this and then head on out to Susquehannock State Park the following week. One other request just came in today to me, Girl Scout Troop 7287 in Royersford. They're looking for an hour to 90-minute program at a dark sky park area. They were considering, first thing she said was, well, we were going to go to Cherry Springs State Park. I said, I don't think that's a real good idea. That's 5 hours away. And if the girls have never camped and you've never done astronomy camping, probably some places a lot closer you could go. I told her we had a star party. We ourselves are having a star party this Saturday at Valley Forge, and she's welcome to join us. But they're looking for somebody to do an hour to 90-minute program some Friday or Saturday evening. They've got a couple of other programs they're already working on. They're meeting with some people from Widener who are going to do a program for them. And there's some sort of merit badge they want to earn, and they're hoping we can help them. So that's my presentation. I'm going to throw it back to Jeremy, but we have Don Nab here to talk to us a little bit about one of the Merrill programs. And then after that, I'll come back to you, Lewis, okay? So let me stop sharing. Stop share. There we go. And you all are back. And Don, talk to us.
Okay. I need the, all right, you could screen share is good. Let me do that. Okay, let me start my slideshow. All right, so for those who don't know me, I am I'm Don Nab. I'm a DVAA member, but that's like my second club. My main club is Chester County Astronomical Society, where I'm the treasurer and the observing chair and the Zoom coordinator and the Night Sky Network coordinator, and my wife is a librarian, so I do a lot for the club. But I'm also the Mideast region chair of the Mideast region. I will talk about that. So as a group, I'm going to tell you about what we're going to do as the Mideast region. Just an idea that one of the other, a president from one of the clubs down in Howard, Maryland came up with. So come to talk about the Constellation Hunter program of the Astronomical League, or the AL, is what it was called. So the league is about 300 clubs, and that's a record right now at 21,000 members. And only a few months ago was 18,000, and it's up to 21,000 now. And it's great to see you guys are breaking 200. Believe it or not, today, our club got 8 new members because we teamed up with the Westchester University Astronomy Club of students. So we gained 8 members today. We're at about 135 or so. So this is Astronomical League website, and it's easy to find. You can search for, I think it's astroleague.org. And there are regions. These are the regions of the Astronomical League, 10 regions, and this is us. So we are the Mideast region, and we call that Merrill, Mideast region Astronomical League. So when you hear someone say, I'm part of Merrill, Merrill is the Mideast region. Now, this is a screen capture from the Astronomical League website. The website is in pretty bad shape overall. It's being redone. It's going to be reissued probably sometime next year. They're going to patch a couple things later this year. But this is the Mideast region page. It shows our states. Now, this guy, Terry Trees, I replaced him 2 years ago. They can't even update this page. It's in that bad shape. But you might recognize this guy down here. I think you all know him. He's our regional representative for Merrill. So there are 40 clubs almost. I think like 39, to say nearly 40 in these states. So I want everyone to know what Merrill is, because it was only a couple of years ago that I found out what Merrill was. And I've been in a club since like 2006, but I didn't know what Merrill was. So now hopefully people know what Merrill means. So, and most, if not all members of these clubs, of these 40 clubs, are Astronomical League members. And you can participate. There are 60 observing programs. This is just a screen capture from that page on the Astronomical League website. There's all kinds of stuff, 60 of them. But as a group, we thought, as far as Merrill, what could we emphasize? And you can't see it exactly down off the page here. We decided to emphasize the Constellation Hunter program, because that's a great thing to do. So many clubs, just like you guys, have new members recently. I mean, it's not just DVAA and CCAS, it's across the whole country. So this Constellation Hunter program will be a great way to people to learn the night sky. And any long-term member who's not yet learned the night sky. doing this is the best thing for your observing skills. You know, you go out, you look up, what do you see? A bunch of stars. And we want to sort of give them a network, a framework, and that's what the constellations are for us. 2 certifications, northern and southern. Of course, we're going to do the northern. And it's to provide an orientation to the sky for novice or experienced astronomers. And the great thing about this club, as being the first one you would do, was observing program. They used to call them observing clubs. I tend to try to call them observing programs. No special equipment is needed. All you need is a sky chart, and it could be your iPhone or your Samsung phone, and a reference for the brighter star names. And again, it's to provide a forum for the novice observers to become familiar, learn to navigate the stars. It's never going to leave you, it's a skill that will never leave you once you learn to navigate the stars, and give a good foundation for moving to other programs. And the great thing about knowing the sky, I see the constellations as old friends. Like in the spring, when I see Leo coming up, it's like I'm seeing a friend I haven't seen for 6 months. Hey, there's Leo. And there's something really nice about knowing the night sky. And here's the easy way to do it. This star map from skymaps.com can be downloaded every month. And this is really pretty much all the information you need to start doing this observing program. You see they list the main stars in it. They give you the shape, south, north, east, west. You know, the ideal way is lie down on your back and put whatever direction you're looking, this at your feet. Binoculars, not required, but especially in our light blue skies, they're very helpful, allow you to see some of the fainter stars. But the one thing they do say, you don't include all the faint stars you see in binoculars, just the main stars, and it makes it pretty easy. So as full of information as at the league, and we'll bop there in a minute when I get through these couple more slides. This is the actual page for the Constellation Hunter program. Again, it scrolls down. There's links to the list. There's links to a form you can use. So what do you need to do? How do you get this? This program under your belt? Observe and sketch all the constellations in the northern sky. Now it's pretty obvious. This is one I did. You don't have to be an artist. I'm not so good at drawing, but I can do a stick figure. I can do dots and lines. So it's not hard to do. It doesn't have to be exact. The darker, the bigger the spot, the brighter the star. So you want to do that. Mark any of the major stars that you see. And it can take a year because constellations roll around over the course of a year. Now you can actually do it much sooner if you wanted to stay up really late or get up before the sun. Because right now we have this fall constellations. If you stay up till like midnight or 2 a.m., you're seeing the winter constellations. And by 4 a.m., Leo is rising, the spring constellation. So if you really want to do, you can do it much faster. But most people take about a year for the constellations to be in the evening sky. That's what I did. So this is the download form you can get from the Astronomical League. But I've made this one, which I think would be a lot more useful. You can put 2 on a page for one thing. It gives you the seeing system here, excellent to poor, transparency, which really is basically the magnitude of the stars you see, or just a 1 to 7. And, you know, a good night is a 7, a crappy night is a 2 or a 3. Can you put your name, the constellation, date? You fill this out for all 39 constellations, and you get the program completed. So 39 constellations. This list is, again, on the website. You can download it. Oh, let me go back one. I went too fast there. And when you finish, you get a really nice lapel pin, which I have here. I can show you them, but there's a picture of mine on my table. Here's my my certificate. This actually goes back to 2009 when I got it. And your name gets published in the Reflector, the quarterly magazine. So it's a fun program. I really enjoyed it. Let me just show you real quickly. Here's the Astronomical League. You get here, astroleague.org. To find more, you go to Observe. And I usually go to programs alphabetically. And I will scroll down here and find Constellation Hunter program. And here's everything you need to know. I've already sent that that form to your Club Alcor, and everything else you can download here. See, here's their sketching form. It's pretty simple. I like mine better. And here's where you get the list. So I think that is, and what I'm going to do, I'm also going to make a page for this on the Merrill website. This is a site that I maintain. I'm going to add a page for the Constellation Hunter Club. We'll have links to all the things you need to find. So I'll be putting that up within a few days. So any questions? I think it'd be fun to get everybody to be wearing one of these in the next star party, and to see a bunch of names from DVAA and CCAS and all the Merrill clubs in the reflector about a year from then. So
Yeah, that's been on my list, Don, and there's no reason not to do it now. So thanks for motivating us. That's great.
Okay. Yep.
Appreciate it.
I'll be doing this. I'll be sending this presentation out to the Alcor and to you, Harold. You can share it if you want.
Thank you.
It'll be in PDF format, so it's easy for people to look at.
Okay.
And,
Will your blank form be with that?
Yes, I will send that also. Yep.
That'd be super. Thank you so
I'll
much.
send all that stuff. Yep.
And
within
thank
a few
you.
days, I'll have the Merrill page set up too.
And it was good to have you with us last week.
Yeah, it was a great. We had like 7 of us from CCAS up there. A couple had to cancel, but we had a great time. That was a wonderful star party.
It was great. It was
I
great.
had to arrange for good weather.
Yep. All right. Well, thank you very much. I'm now going to give the floor to Jeremy, who can introduce our guest, and I'm looking forward to hearing from Paul. And take it away, Jeremy.
All right. Thanks so much, Harold. I'm actually having some computer trouble here. My Zoom seems to be frozen up. Can everybody hear me?
Yes.
Yes.
Right. So it might just be an issue with my screen. So, all right. Well, here we are. So I just want to remind everyone, if you're not the invited speaker, please mute yourself. So that way we'll keep the sound level down. So I'm delighted this evening to introduce Paul Halpern, who is our evening's invited speaker. So Paul is a professor of physics and a fellow in the humanities at the University of the Sciences in Philadelphia. So he completed his PhD in theoretical physics at the State University of New York in Stony Brook. And he also did his undergraduate work at Temple University, right in our area. So he's the author of a number of popular science books and articles. Among his books are The Great Beyond, Cosmic Wormholes, The Cyclical Serpent, What's Science Ever Done for Us, Einstein's Dice and Schrodinger's Cat, The Quantum Labyrinth, Countdown to Apocalypse, and his brand new book is called Flashes of Creation. So I was interested to read that Paul had appeared in the Simpsons 20th anniversary special in 3D on ice. Wondering what that was. And he's also frequently been interviewed for a number of radio and television shows, including PBS and NPR. Paul also received a John Simon Guggenheim Foundation Award in 2002. So tonight, Paul is here to share a presentation on his latest book entitled Flashes of Creation. So please join me in welcoming Dr. Paul Halpern.
So can everybody hear me?
Yes.
Great, great. Well, I wanted to thank Jeremy for the kind introduction and for inviting me to the meeting. I'm very excited to be here at DVAA. Of course, it'd be nice to be able to do things live again, but we have to be safe. I don't live too far from Radnor, so but hopefully next time, maybe for a future book or something, it'll be nice to meet all of you live. But this is exciting to be able to talk via Zoom. So anyway, I wanted to say a little bit about my recent book, Flashes of Creation, and the lives and work of George Gamows and Fred Hoyle, who some of you might remember or hearing about at some point or read their books, and others of you might not know who they are. So I wanted to explain who they are. So let me go back to ancient times and talk a little bit about questions that have been puzzling people, particularly astronomers, but many other people since antiquity. First of all, did time have a beginning? People have been debating that for millennia. And if time does have a beginning, what exactly happened at that Genesis? What happened to bring the universe into being? Or in ancient times, what happened to bring Earth into being, people wondered. How did the stuff of the cosmos emerge? Like, where did it come from? Was there stuff before that? How large is the universe? What is its extent? What makes up the universe? And then finally, the ultimate question, will the universe someday perish, or will it last forever? Might there be future cycles of the universe? These have been debated since antiquity. Now, until relatively recent in our timeline, there was really no accurate way of answering these questions scientifically. So what you had is various philosophers debating each other about the topic. So you might have Pythagoreans talking about the world being made of numbers and everything being made up of numbers added to each other. So that's why the Pythagoreans thought that there was a counter Earth to Earth, because they believed that there were exactly 10 heavenly bodies, including the dome of the constellations. Speaking of constellations, they counted that as one heavenly body, the dome of the stars. And because they liked the number 10, simply, that was their method. They liked the number 10. So they said there were 10 objects in the universe, from Earth to the observable planets, to the dome of the stars, the moon, the sun, and then a counter Earth to make up the number 10. And they had no evidence for a counter Earth, but they postulated it just because it fit their system, their philosophical system. And people who followed Democritus thought that everything was made of very small bits of things, which he called atoms, meaning unbreakable things that you couldn't cut into smaller parts. So this was how philosophers examined the nature of the universe at that time, but not particularly scientific. Now, let's look at about 100 to 110 years ago. There were many revolutions in science, and it's pretty remarkable to me that a lot of these revolutions happened within the last century or century and a decade or so. So there are people still alive today who were born before these revolutions, remarkably. The first revolution is the relativity revolution, including special relativity, which is Einstein's theory of high speeds, and general relativity, which is Einstein's theory of high gravitational fields. Then there's quantum physics, starting with the Bohr model of the atom, but then extended to equations describing the quantum world. And that led into atomic physics and then eventually nuclear physics. So nuclear physics, we're talking about the 1930s when all the breakthroughs took place. And that was very important for understanding the universe and for understanding stars. Nuclear physics was essential. And here we see two physicists who are key to these times. Albert Einstein, the founder of not just special relativity and general relativity, but also a lot of quantum mechanics, because he postulated the photoelectric effect. And Niels Bohr, who created the first somewhat accurate atomic model, and that was modified and then later converted into a probability model. And he continued to organize the quantum community, and then he made major contributions to nuclear physics. So there were two monumental physicists who both got their Nobel Prizes about 100 years ago. So once again, relatively recently in history. Now let's leap ahead to from the beginning of the century to 1915, which was an important year for Einsteinian relativity. That's when Einstein published his general theory of relativity. So for any of you who read German, here's the paper. And that is his theory of gravitation. And that was also the year of the birth of somebody named Fred Hoyle, British physicist, who was born in an unlikely part of England, Bingley, Yorkshire, which is a relatively rural part of England. Bingley is a small town near Bradford, which is an industrial area in northern England. So it wasn't a very likely place for an intellectual who would make major contributions to physics to be born. Just because of the British class system, a lot of great scientists were more likely to be born in the South. This was something that Fred Hoyle was very proud of, that he made it without having any class distinction. He was, of the working class family, but was very, very bright, and made it to Cambridge, and from there proceeded to revolutionize astrophysics. So here's a plaque marking his birthplace, which I was lucky enough to visit before the pandemic. So the research for my book turned out to be timed very well. I did most of the research in 2019, fall of 2019, when I visited England and Cambridge and Bingley and traveled around, and no one knew what would happen the following year, of course. And then if I had planned the research trip the following year, I wouldn't have been as successful because I wouldn't have been able to go to these places. Now, back to general relativity. Wanted to sum up general relativity in a nutshell. These are the words of the great physicist John Wheeler: space tells matter how to move, matter tells space how to curve. That's a very succinct explanation of general relativity. And I had the pleasure of meeting Professor Wheeler, and he essentially said this to me during the meeting. He was very proud of his expressions, of his books, and a very charming person. And his son still actually lives in the main line, so a very nice fellow too, a physician. So anyway, back to this expression. If you take a star, according to general relativity, the star warps space-time in its vicinity. So we see something like a well. So it's like throwing an object into a basin and making ripples and creating a dent. And then if we look at other objects in the vicinity, because of the curvature, these objects have to travel in elliptical orbits. They do not travel in straight lines. So if they try to take the straightest line, which is a geodesic, they travel in elliptical orbits. This is the equivalent of Newton's theory of gravity as kind of an invisible string linking objects, but it's much more satisfactory because it happens at each point. So we know exactly how the sun distorts space-time at that point. We know how the Earth and other planets react to space-time at other points. You don't have to imagine something in between. Now, you can use general relativity to try to understand local objects such as stars, or you can use it to try to understand the universe itself. So one of the first solutions was by Carl Schwarzschild, described what became known as black holes. But one of the subsequent solutions was developed by Einstein himself. Einstein wanted to look at the entire universe and explain why the whole universe is stable. Now, you might be scratching your head and saying, what do you mean it's stable? The universe is expanding. So we now know that it's expanding. But Einstein thought that it was stable because that's what Newton said. And Einstein respected Newton. He disagreed with some things that Newton said. He didn't want space and time to be absolute, but he did want the universe as a whole on the largest scale to be stable because he thought that the stars, even though they move through space, space itself would stay fixed. So that was his opinion. And he also had other philosophical reasons for a stable universe. So he put in the conditions for a stable universe into his equations and developed mathematically a solution And then he tested out the solution and decided to tinker with how much matter is in the universe. And much to his dismay, if you changed the amount of matter in the universe just very, very slightly, the universe model he had either collapsed or expanded. It blew up or shrunk down. And he was absolutely aghast by that. He said to himself, this can't be right. This is a poor solution because it shows that the universe is unstable. It's exactly what I didn't want. I wanted a stable solution. So finally, he decided, it's sort of a last-ditch effort, to add a kind of fudge factor to his equations, and it's called the cosmological constant term. And that is kind of like a scaffolding that keeps everything stable. So it acts as a kind of anti-gravity that balances out gravity and keeps the universe stable. So it's very inelegant. It's like taking a fancy building that's noted for its architecture and then putting steel girders around it to keep the building stable. It's really not a good idea. But Einstein felt kind of desperate to do this, and that became the cosmological constant term, and that led to stable solutions. So he was very happy about that. But then a couple years later in 1922, Alexander Friedmann came along. He was a Russian physicist who worked in the city then known as Leningrad. Before that, it was known as St. Petersburg, and now it's also known as St. Petersburg, but is briefly known as Leningrad because of the first leader of the Soviet Union passing away, and they named the city after him briefly. Well, briefly meaning for decades, but now it's back to St. Petersburg. Well, anyway, so Alexander Friedmann was trained as a meteorologist and decided to pick up cosmology as a kind of avocation, not exactly a hobby because he was a professor, but as kind of a sideline. So his main area of study was taking hot air balloons and measuring the atmosphere at different levels and testing theories of the atmosphere. But then he took Einstein's equation, decided to leave out the cosmological constant and see what happens and test out different solutions. And he discovered that in all cases, the universe blows up like a balloon. And since he was into hot air balloons, that was kind of a remarkable analogy that he used that. So if we imagine, at that time, they were unsure about galaxies outside of the Milky Way. There was a great debate as to whether or not the Milky Way was the only galaxy, or if the nebulae in the Milky Way, if some of those were galaxies in their own right. And of course, that turned out to be the case. What was known as the Andromeda Nebula turned out to be the Andromeda Galaxy. And many other nebulae turned out to be galaxies. But anyway, if we look at these galaxies, we take them to be galaxies, and we blow up the universe, if it expands, according to one of Friedmann's solutions, the galaxies get further and further apart. So we now call that the Big Bang model of the universe. But that was a term that was invented later, as I'll show, by Fred Hoyle. So enter into the picture George Gamows, who was a young man from Odessa, which is now in Ukraine. It's not in Russia, but at that time it was part of the Russian Empire. He was a very bright student, very bright young man, and he excelled in his studies. And his father had a connection with somebody at the University of Leningrad. So Gamows went up there. He did some meteorological projects and some military-related projects, but then Friedmann taught him in a general relativity course. So then he took a course in general relativity with Friedmann, and became fascinated by the study of cosmology. But sadly, Friedmann died before Gamow had a chance to work with him on research projects. In 1925, he took a balloon up into the atmosphere and got very cold and got ill. And sometime later, he developed typhoid. I'm not sure if they were connected. The two were connected. And there's different theories about why he developed typhoid. But he died at a fairly young age. He died in his 30s. And Gamow was heartbroken. So Gamow ended up having to do a thesis in quantum physics instead, which actually turned out to be a good thing because Gamow also made his mark in quantum physics and nuclear physics. So he was an expert in all those things. So now let's go to the United States, where we find Edwin Hubble in 1929 making measurements of galaxies, and he already had determined that Andromeda and a number of other nebulae were outside of the Milky Way. They were still called nebulae, but some people started calling them galaxies or island universes. And he made a plot of their distance using the method of Cepheid variable stars. Cepheid variables are standard candles, and they can be used to ascertain distances, as I'm sure many of you know. And he used the Doppler shift method of the light from the galaxies to measure their expansion rate, or rather their recession rate, how fast they were moving away from us. And he found that almost all the galaxies in his survey were moving away from us, meaning they had redshifts. And the redshifts were greater and greater the further the distance. Now, I have to give credit here to Henrietta Leavitt, who was an astronomer at Harvard, who discovered the Cepheid variable method for measuring distances, and also Vestos Liffer, who was another astronomer who took careful measurements of Doppler shifts of galaxies and probably would have been able to discover the expansion of the universe himself if he had leapt to that conclusion. But when Hubble took these measurements, Hubble was a prestigious scientist working at Mount Wilson Observatory in California, and everybody listened to him and immediately concluded that the universe is expanding because the galaxies are moving away faster and faster the farther away they are. And it matches up with that balloon model that I showed you earlier of Friedmann. So people recalled Friedmann. They also recalled the work of someone named Lemaitre, which I'll talk about in a minute. Now, by the way, Hubble was also a fantastic basketball player. Not many people know this, but he led the University of Chicago team to victory and then became a basketball coach at a high school. So luckily he wasn't so successful that he didn't study astronomy because he was an important astronomer. So it's good that he left basketball and went to astronomy. Now here's his data. And you see, you can draw a nice straight line fit through these galaxies if you look at distance versus velocity. And this is called Hubble's law, later amended to be called the Hubble-Lemaitre law, named after this fellow on the left, Father George Lemaitre, who was a Belgian priest and a cosmologist. And he insisted that the two should be kept separate. Science and religion should not be mixed, he said. So he developed a model similar to Friedmann. He said that the universe expands, and he hypothesized, he went a step further from Friedmann, and hypothesized that the universe began very, very small, which he called the primeval atom. And at the time, he originally suggested that the universe is expanding. Einstein was dubious, but then later, after Hubble's findings, Einstein became a believer in expanding universe and reportedly told George Gamow that the cosmological constant was the greatest blunder he ever made in his life, scientific blunder, that he shouldn't ever have introduced it, because if he hadn't introduced it, he would have predicted the expansion of the universe. So the two of them worked together briefly and had great respect for each other. Now here's Lemaitre's book, The Primeval Atom, and he did not call it the Big Bang. He called it Primeval Atom. And just the hypothesis is that all the matter in the universe came from a single atom that started to expand and broke up from the giant atom into the various elements. Well, the problem with that idea is that you have to start with one atom and it breaks up into different elements. Is if you look at what's the most common element in the universe, the most common element is hydrogen. And hydrogen is, of course, the simplest element. So if you think that the elements started top down from the most complex elements to the simplest, it's a very unlikely hypothesis that hydrogen would be the most common. It'd be much more likely for uranium to be the most common element in the universe, or even larger atoms than that. Well, there are no larger atoms in nature than uranium, and hydrogen is by far the most common, and then helium is the second most common. So that suggests a bottom-up approach, that you start with hydrogen, and hydrogen builds up to other things. And that process is called nucleosynthesis. So this was something that was debated for a while. How, first of all, the question is, how do stars shine? And then a related question, how do elements form? And they turn out to be closely connected questions. The first one to speculate that stars shine because of hydrogen converting into helium was Arthur Eddington, famous astronomer. But Arthur Eddington supposed that 4 hydrogen nuclei got together simultaneously and formed helium in stars. Well, that is virtually impossible to happen. It's very, very unlikely for hydrogen atoms, 4 of them, to have a head-on collision at the same time. It doesn't happen. But as it turns out, there is a multi-step process for hydrogen to convert into helium, which is one of the ways that stars shine, the proton-proton cycle. So that was known by the time of the 1930s. A pioneer in that area was Hans Baade, a nuclear physicist, showed that stars shine because of 2 cycles, the proton-proton cycle and another cycle called carbon-nitrogen-oxygen cycle that also turns hydrogen into helium by a more complex method. So that was known, but then it wasn't really known how the higher elements are formed. How does carbon itself form, or the higher elements? Well, so George Gamow got into nuclear physicists. Here he is with John Cockcroft, who is a British nuclear physicist who developed some of the first colliders. So he was really interested in nuclear physics. And Gamow developed the idea that quantum mechanics applies to nuclear physics, and that explains how hydrogen can get together, even though hydrogen nuclei are positive. So hydrogen nuclei are protons, which are positive. Normally, 2 positive particles would repel each other, but under extremely hot conditions, they can tunnel through the energy barrier between them. So if you map out the energy of them, there's a barrier. The barrier has to do with the repulsion. They can tunnel through the barrier and unite. And then we now know that what keeps the protons together is something called the strong force. So once they get through the barrier, the strong force pulls the protons together. And then one of the protons immediately decays and becomes a neutron through a beta decay process. And that becomes heavy hydrogen, or deuterium. Now, Gamow developed that idea. He also developed a reverse idea, which says how atoms can give off particles, emit particles through a similar process called alpha decay. And that was used, those ideas were used to create some of the first particle colliders, was they found that they could use the process of quantum tunneling to hit targets, to aim particles at targets and have the particles cross energy barriers through quantum tunneling and then break the targets apart, which was the work of people like Ernest Rutherford and others. Their phenomenal work in showing how you can transmute elements from one to the other. Now, Gamow decided at one point that he needed to escape Russia, which was then known as the Soviet Union, because under Stalin in the 1920s, especially in the late 1920s, the Soviet Union became more and more politically rigid, ideological, and finally science had to be interpreted through Stalinist interpretation, which put a damper on scientific efforts because they had to interpret everything a certain way. So Gamow found that untenable, unworkable. So he and his young wife, Ro Gamow, R-H-O, decided to escape using the Black Sea crossing to Turkey. And they had a rubber kayak. And this is a picture actually that Gamow took later with his second wife, but it's the only picture I could find of Gamow in a kayak. No one was there when he tried to escape, we think, unless there were some, what is now known as the KGB agents photographing him. But we don't have a photograph of that. But he and his wife loaded up a kayak with food, chocolate, brandy to pass the time. They set sail into the Black Sea. It was sunny weather the first day. The next day there was stormy weather. They were forced to head back to shore. Luckily, their excuse that they were just going on a leisure expedition was bought by the security guards, and no one arrested him. But then he got a formal invitation, thanks to Niels Bohr, to the 1933 Solvay conference in Brussels as the representative of the Soviet government, of Soviet science. And he managed to convince the Soviet government that he needed to bring his wife because she was his scientific collaborator. So they went to Solvay conference. Gamow is in the back row here. So he's one of the people in this picture, which includes people like Marie Curie and others. Einstein was not at this conference. By then, Einstein had escaped Europe for the United States because of the rise of the Nazis. So he was invited to this conference, but he had escaped. Or he had left Europe at the time. And then Gamow had escaped to Europe. He talked to Marie Curie, who put him up in her lab, let him work at her lab in Paris for a while. But then he decided, on Bohr's advice, that Europe wasn't safe enough because of the Stalinists and the Nazis and so forth. So he decided to move to the United States. He went first to University of Michigan, where he gave some talks. And then he got invited to George Washington University to be a professor. So he promptly got a ticket to Seattle, Washington, before realizing that George Washington University is in Washington, D.C. So he luckily exchanged a ticket and went to the right Washington. And he lived for a number of years in Bethesda, which is a city near Washington, D.C., and worked at George Washington University. Meanwhile, around this time, 1930s, Fred Hoyle got first a PhD position at Cambridge, where he talked to people such as Eddington and Dirac. And Eddington was very told him about Gamows' work. So he learned about Gamows' nuclear work and was very impressed. So Hoyle was a big fan of Gamow. Gamow was about a decade behind him, age-wise, or a decade ahead of him, a decade older, I should say. And Hoyle was very impressed by Gamows' accomplishments in nuclear physics, but wanted to take them further. And then he was granted in 1939 a professorship at Cambridge, but then he had to take a leave because of the war efforts. World War II started in 1939. So from 1939 to 1945, he was involved in the British military effort before returning to Cambridge as a professor in 1945, when the war was over. Now, right after the war was over, he went on a military mission to the United States, and there he met with astronomer Walter Baade, and Walter Baade told him of his remarkable new theory about generations of stars, population 1 stars and population 2 stars. Population 1 stars are stars like the sun, and ones which are metal rich. Now, some of you may know, but maybe not all of you, metals are any elements beyond helium and hydrogen in formal astronomical parlance. So, so some stars are metal rich, like the sun has, not a huge amount, but the sun has some, higher elements. And some stars are metal poor, meaning that you don't find any spectroscopic evidence of any elements beyond hydrogen and helium. And Walter Baade called them population 2 stars. And his theory was that population 2 stars had more catastrophic ends, exploded in supernova explosions, and released the materials, which included some metals, into space, and these were taken up by new generation of stars. So he sketched out that theory, but the theory was much more developed by Fred Hoyle. Fred Hoyle thought that was a fascinating idea and decided to investigate the possibility that elements are built up in the cores of dying stars. So Hoyle's brilliant idea is that when massive stars, much heavier than the sun, die, particularly these population 2 stars that preceded our generation, so earlier generations of stars, that when they die, they can no longer burn hydrogen simply in fusion process. So therefore they have a layer of helium. And then Hoyle surmised that somehow the helium started burning and then formed heavier elements than that, such as carbon. And then that could burn and form heavier elements than that. And then in the very core of the star, in the center, the temperatures are higher and higher. And as you get to closer and closer to the very center of the star, temperatures are so high that elements up to iron and nickel can be formed. So iron and nickel are the heaviest elements that could be formed in these stars. Well, what about higher elements such as uranium and so forth? And all the elements in between iron and uranium. Well, Hoyle surmised that during supernova explosions, temperatures go up even further, and that enables fusion processes to happen, which are impossible in stars. And in the brief instant of that explosion, suddenly all the elements up to uranium can be formed, and then everything is released into space. So that's why you have a small portion of uranium and elements higher than iron in space. So that was his theory, and it's revolutionary theory, remarkable theory. It should have won him the Nobel Prize, but there are a variety of reasons, which I talk about in my book. why Hoyle never got the Nobel Prize. And Gamows should have got the Nobel Prize too. So both of them were Nobel Prize worthy physicists, but both were nominated, but neither got the prize. And I speculate about reasons in my book. So around the same time Hoyle proposed this, he wanted to take a break and see a movie. So he and his friends and buddies from the military, Herman Bondi and Thomas Gold, Thomas Gold and Herman Bondi, rather, this is Gold and this is Bondi, were sitting in a movie theater, and they decided to watch a horror film. And there was a popular film at the time called Dead of Night, which I highly recommend. It's a very scary film, and it's about somebody who goes to a house in the countryside, and as soon as he goes to the house, he tells everybody who's gathered at the house for kind of a party or kind of a get-together. He says, I have a feeling I know all of you. I have a feeling that I had a dream about all of you. It's very strange. And I also have a feeling that something horrible happened, but I don't remember what. And then the film proceeds, and the guests start telling these horror stories. And most of the film are these horror stories that guests are telling about various things. And then the film culminates in the scariest story of all, which is about a ventriloquist played by Michael Redgrave, the famous actor. And he is haunted by his dummy named Hugo. Hugo turns out to have his own very evil personality. So that was the start of many, many films where a doll or a dummy comes to life and becomes evil. So a popular theme. This was one of the first ones. So Hugo is very evil and does terrible things at the end of the movie. And the main character at the end wakes up and realizes that the whole thing was a nightmare, luckily. But then he gets a phone call and gets an invitation to the same country house and doesn't realize that he had been to that country house before and drives out there, and the whole thing starts all over again. So the whole film is a cycle. So then after the film, they all went back to Herman Bondi's apartment at Cambridge, and they had some drinks. And over the drinks, they had this discussion. And Tommy Gold said, what if the universe is that way? What if the universe is always the same fundamentally, that it goes through cycles, but just like that movie, wherever you walk into the movie, you pretty much can see the same thing again and again. What if the universe is static over time? Now, they all knew that the universe expands, so they had to come up with a way that the universe can expand but renew itself. Well, one way is if the universe starts contracting again, but they didn't really believe in that. They thought the expansion would keep going. Another way is to imagine that new galaxies fill in the gaps between the old galaxies. So that's the idea they came up with, called steady state. And Hoyle came up with one model of steady state. Bondi and Gold came out with a competing model because they had slight differences as to what created the matter. Hoyle came up with the idea that a quantum field created small particles very, very slowly. And today we know that that theory is actually true, that quantum fields on a small level can create particles as long as the particles are short-lived. These are called virtual particles that emerge from the quantum vacuum and then return to the quantum vacuum. So Hoyle was right on the mark there. He called this a creation field, but he said the particles would emerge. They'd at some point gravitationally attract each other, start forming larger and larger clumps. Those clumps would eventually be large enough to burn hydrogen in a fusion process, become burning stars, and then those stars would form galaxies, and then ultimately fill in the gaps left behind by the old galaxies. So this is very different from the Big Bang idea that the galaxies are constantly separating. So I like to think of the difference between the steady state and the Big Bang model. The difference is a little bit like a stadium where people have to socially distance. So imagine there's a stadium where all the rows are occupied by people watching a music concert. And then all of a sudden on a loudspeaker, they say, you need to sit, you people are all too close. You need to sit at least a row apart from each other. So the people in the first row stay there. The people in the second row have to move to the third row. But then the people in the third row have to move to the fifth row. And they keep going and going. So eventually they all spread out and there are gaps between the rows. And that's a little bit like the Big Bang theory, that there are gaps between the galaxies. The steady state model, on the other hand, imagines that what if after they make the announcement, these teenagers who want to see the concert cheaply run in and fill up all the empty rows that the people with tickets had previously filled. So they're going to fill in the second row and so forth, even though it's not supposed to be that way. And then the stadium will look the same because all the rows will be filled again. So the new people would fill in the gaps left by the older people. So that's a way of thinking about that. So I mentioned already Hoyle's method of making elements that he proposed in the higher elements, I should say, 1946. And he continued working on that idea. But then Gamow, with his research assistant Ralph Alpher at GWU, proposed a different way. They said, what if all the elements were created in the hot early universe, when the universe was in the millions of degrees, and they speculated that was hot enough to create all the elements from hydrogen all the way up to uranium. So they wrote a paper like that. Gamow had a wicked sense of humor. He loved puns, and he thought, well, I could call this Alpha and Gamow. That's a little bit like the first and third Greek letter, alpha, gamma. Wonder if I can add Hans Beta to the paper, even though Hans Beta didn't do any work, so that it's alpha, beta, gamma, like the first Greek letters. Well, that's what he did, just to make the pun. Hans Beta was kind of amused by that. He got his name on a paper for free, and he was a friend of Gamow, so it didn't really create a problem. But Alpha was really upset because he was the one who did all the calculations for the paper. And now he was, instead of getting half credit, which a PhD student kind of expects that his advisor would get credit, he got a third credit. So he was, for his lifetime, a little bit upset that Gamow made that pun. And the paper was published coincidentally on April Fool's Day. Now, Gamow and Alpha called the original material of the universe that, for the first step they said is it kind of decomposed into neutrons. They called that LEM, Y-L-E-M, which is a medieval Latin name for matter, which stems from an ancient Greek name for matter. So Alpha found this in a dictionary, I suppose, and decided to call the early stuff of the universe LEM. And they celebrated the publication of their paper by taking a bottle of liqueur and relabeling it LEM and having some drinks. And unfortunately, Gamow turned out to be a very, very heavy drinker, and that led later to a lot of health problems. But this was their toast. And this bottle, by the way, is now in the Smithsonian Institution Museum. in the Air and Space Museum as part of the cosmology exhibit. Now, Alpha gave a talk about their method for producing the elements. And in the talk, he said all the elements from helium to uranium could be produced in the Big Bang during the first 5 minutes of the universe. And this was a cartoon that appeared in Washington Post by the great cartoonist Herbert Bloch, or Herb Bloch. And this is a nuclear weapon because that was the start of the nuclear age. We're talking about around 1949. And nuclear weapons were very much on people's mind. And the nuclear weapon is kind of perplexed how that could happen so quickly. The whole universe all the elements in the universe could be made the first 5 minutes. Now, some of you may have heard about the book by Steven Weinberg, The First 3 Minutes, which is about how the elements up to helium are created. So, and that's because we no longer believe that all the elements were created in the Big Bang. Only helium was created in large quantities in the Big Bang. And that's because as the universe expands, it cools very rapidly. So right after the Big Bang, the universe is expanding and cooling very rapidly. Now it's still really hot. So it's still scalding hot in the first 5 minutes, but it's not quite hot enough after the first couple of minutes to allow for helium burning. Why is that? Because helium burning is really complicated. It's one of the hardest types of fusion to do. You need for helium burning, you need 2 helium atoms to collide. That's okay. Then they produce beryllium-8. But the problem is beryllium-8 is extremely unstable. It decays within some trillionths of a second. So normally beryllium just decays. So if you produce beryllium-8 under anything but extremely, extremely hot conditions, even hotter than the Big Bang, it will decay. So they found an impasse. This is a missing rung on their element ladder. So, so the physicist Turkovich wrote a letter to Alpha and said, there's a problem with your theory. You can't do helium burning. And Alpha was really upset and tried to find a way around it, but he couldn't really find a way around it. Now, Hoyle was the one who found a way around it. Hoyle said at some point, well, carbon exists, therefore there must be a way of producing it because we're all made of carbon, right? So there must be a way of producing carbon. So Hoyle added to another physicist's explanation and came up with a complete explanation for how carbon-12 is produced. So the helium gets together in the dying core of a hot star. So you need a hot stellar core that heats up to hundreds of millions of degrees. In that core, beryllium is produced, but under those circumstances, it's possible for quantum tunneling to occur. These two, another helium to get together with the beryllium, form a stable quantum state, which transitions easily into a quantum state of carbon. And he predicted which quantum state of carbon that would be. And that was later tested and shown to be a valid quantum state of carbon. So that confirmed his theory of how carbon is produced. So that was a brilliant idea. It won the Nobel Prize, but not for Hoyle. It won it for Willie Fowler, who was the one who discovered that state of carbon and proved Hoyle's idea. And in my book, I talk about the consequences of that fact that Fowler won the prize instead of Hoyle and reasons for that. It was a real scandal. 1949 is also the year that Hoyle gets on BBC radio and he became this great popularizer of physics. And He gave a talk about steady state versus the rival model, and not particularly referring to Gamows' idea, but just referring to the general idea that the universe expanded from a small point. He made up the term Big Bang, and he mocked it. He said, well, it's ridiculous to think that all the matter in the universe came from a giant explosion in the past. Wouldn't it be better to come up with an idea where matter is very slowly trickling into the universe with a steady process? So he argued very persuasively, I should say, that steady state theory made more sense. And he convinced a lot of people. So both of them are great popularizers. Their books came out roughly the same time. Gamows' The Creation of the Universe, Hoyle's The Nature of the Universe. Gamows' book, of course, emphasized what was known as the Big Bang, and then Hoyle's book emphasized the steady state model. So if you were browsing on a newsstand or bookstore, you could pick up these cheap paperback books. Paperbacks were all the rage in the 1950s. So lots of people would buy these paperbacks and then educate themselves about the competing theories of the universe. That wasn't everything Hoyle and Gamow wrote. They became major science popularizers and science fiction writers. Hoyle developed the Mr. Tompkins series, which imagined a bank clerk going to different places and experiencing the extreme situations of quantum physics and relativity. And these visits were in his dreams, I should say. And that enlightened people about quantum physics and relativity. Hoyle also wrote 1, 2, 3, Infinity, which is a book that influenced me very much when I was a child, a book about various aspects of science. Hoyle, those two were by Gamow, I should say. Hoyle wrote The Black Cloud, which is a classic science fiction novel about alien life, and A for Andromeda, the screenplay for that, which is a television series about aliens coming to Earth. He was really interested in the idea of alien life. Gamow illustrated his books with funny cartoons. He picked up drawing cartoons when he was in Russia because he had a friend who did sketches. And then he really started doing this a lot when he was working with Niels Bohr. And he drew a series of cartoons in which Bohr was Mickey Mouse and illustrating quantum physics that way. So, and then here's a cartoon he drew about the race for nuclear for the hydrogen bomb with Ulam and Teller, who were the main people behind the hydrogen bomb. So at that point, the steady state theory was a very viable theory. It was a testable theory. And one selling point for it was that it was much easier to imagine a universe lasting forever than being only 3 billion years old, which was the estimate at the time for the age of the Big Bang universe, because they weren't really sure about Hubble's constant, the rate of expansion. So estimates for the age of the universe were very lowball then, 2 to 3 billion years, much younger than its stars, which made no sense at all. So until they got the estimates of the age of the universe right, a lot of people were dubious about the Big Bang. And the battle was international. Pope Pius endorsed the Big Bang, much to the chagrin of Lemaitre, pictured here, who's urged the Pope not to mix science with religion. And the Astronomer Royal of the UK endorsed the steady state theory. So it became really the main British theory during the 1950s. So I'm going to stop my talk here with the question, how would the battle be resolved? And the hint is this device here, which some of you may recognize, which is in Holmdel, New Jersey, radio telescope. And it was an accidental discovery in 1964 by two great physicists, Bob Wilson and Arno Penzias, both of whom I had the pleasure to interview for my book. Wilson is now at Harvard, and Penzias is retired and in San Francisco. And I interviewed them and got to hear Bob Wilson's recount of the great discovery that led to the resolution of the battle between the Big Bang and the steady state. So I'm going to stop here because my wife's advice to me about talks is don't give too much away. You want people to read the book also. So there's a lot more in the book about their personalities, their quirks, and what happened after. Much of the book takes place after the 1964 discovery and what happens afterwards. So please check out my book, Flashes of Creation, for more about the fascinating history of the quest to understand the Big Bang. And by the way, if you want a personally autographed copy, you can go to Main Point Books in Wayne. I signed some books there already. But if you want it personally autographed, just go to the store manager and or email him. His name is Ben, and say, I want Paul Halpern to personally autograph my book. You can even say to whom, what the inscription should be, and then I'll go out to Main Point and personally autograph the book, and then it will be sent to you. So that's my special way of autographing, since I can't be with you live. That's the next best thing, and you support a great independent bookstore. So I will stop here and open up the floor if there's any questions.
Thanks, Paul. Speak up, folks. Anybody have any questions?
Well, the question you asked, of course, was the cosmic microwave background, right? So it is ultimately discovered, right? You know, the radio waves that were noise that suddenly was what the hell's with this, and turned out not to be noise, right? So.
Yes, exactly. I figured most of you would pick up on what that instrument was, which it's a Homedale antenna radio telescope. Yeah. And you can actually visit it. I visited it myself. You drive out there to what used to be Bell Labs, and I went out there before the pandemic, and it's behind, supposedly in a secure area, but I went into the offices and they said, oh, just go out there. You could just walk to it. So I walked through the fence, and then I heard this loud music blaring. I was like, what is this? And then I identified the source of the loud music blaring from a giant, what looked like a giant horn. And that turned out to be this. The music was actually blaring from the horn antenna. I went up to the cabin, and the spectroscope was removed and replaced by some kind of sound playing device. And they were using it for a company picnic. I thought that was a little bit sacrilege to use something that discovered the Big Bang Theory, proved the Big Bang Theory, using it as a speaker system for a picnic. But I didn't say anything because I was grateful to be up there. And then I found out later that the inside stuff, the detector was at the part of it was at the Smithsonian, part of it was at a museum in Munich. It was donated to that museum. So it's all scattered, but the actual the antenna is still there to observe, and there's a historic plaque there.
Cool.
Paul, one thing that falls out of my brain from time to time is an explanation as to how they know Cepheid variables are a candle. Can you give me the short version so I'll remember it for the next few years?
Well, the short version is there's a relationship between their period and their luminosity, and that, let's see if I can think of why that's so.
Weren't they in clusters? So they're all at the same distance?
Well, they're not. Cepheids, the original way to determine their distance had to do with that fact, the closer Cepheids, but the distant Cepheids, you measure the distance. They're not all at the same distance because they're in different galaxies. So then you infer their distance because you know the relationship for the closer Cepheids between their luminosity and their period.
Thanks. And by the way, Lewis, you have to clean the erasers for having spoiled the surprise.
I'm really sorry. Where does one go to clean erasers, by the way?
We'll figure it out.
I didn't think of that as much of a spoiler. I didn't want to say something because then I would have to say a lot, because then I would have to go through the whole explanation. So I thought I'd leave it as a minor mystery, but I figured everybody would know a little bit about the history of the discovery of the cosmic microwave background.
I think the personalities of the scientists is always fascinating. Bill Bryson writes about that too in his short history of nearly everything. I think it's great when you can sort of talk about not just the discovery, but the people who made the discovery and what their lives were like, and you can sort of see how that worked out.
Yeah, my book is mostly based on interviews and archival material. In fact, I interviewed several Nobel Prize winners. One person who won the Nobel Prize a few weeks after I interviewed him, Jim Peebles. So I was lucky to interview him. And then, I run an event at Princeton. I'm involved in the History of Science group, and there was an event commemorating Peebles' advisor, who's Robert Dickey, who was also involved in interpreting the cosmic microwave background. And we had a plaque ceremony. And after the plaque ceremony, both Bob Wilson and Jim Peebles were invited to the dinner, and at their table there was an empty seat. I sat down, so I was at a table with Jim Peebles' wife Allison, Bob Wilson, and I think one other person. And I said, I know you've told this story before, guys, but tell me exactly what happens when you, Bob Wilson, found the hiss and it was reported to the Dickey group, which Jim Peebles was involved in. So the two of them told the story again, which they've told like a billion times, but I felt so privileged to hear it from the two men who were involved, because Wilson was in the room when Penzias made the phone call to Bob Dickey, and Peebles was in the room when Dickey received the phone call. So
that's great.
It was really firsthand.
That's fabulous.
Yeah. And Penzias, by the way, not many people know this. Sadly, he has some type of dementia, but I interviewed him knowing that, and he still talked a lot about his early life and gave me some insight. So I was able to use some quotes in the book, and his personality was so warm and effusive, and he was so happy that I called him. And he was telling me all these stories. The problem is he kept stopping in the middle of stories because there were a lot of things he couldn't remember. So, but I felt really privileged to call him and talk to him.
Any other questions for Paul?
It was great, though.
Thank you.
It was a great presentation.
Thank you. I appreciate that.
Well, Paul, I'll tell you, the Delaware Astronomy Society has a book club, and I'm going to sort of push your book and see if we can put it on the list, and maybe you'll join us there. Those are virtual meetings.
Okay, so you're not at what's Mount Cuba?
Yes.
I don't know where they are. I have never
They're
been.
Mount Cuba for sure.
Oh, okay.
Because I've been
Yeah.
to Mount Cuba.
Robert Treblecock's on the meeting here. He's in the group. Robert, where do you guys meet when it's not COVID?
It's Mount Cuba, and
It's good because I get a little bit of altitude sickness when I go up to Mount Cuba because
yeah, Paul's talked to us at least twice already, and we've reviewed one of your books at the.
I love the Delaware group. I've been to a lot of the groups in the tri-state area. I really love talking to amateur astronomy groups. So I'm wondering that the Chester group that was talked about earlier, is that the one that meets in Westchester, or is that a different group? The Chester County Astronomical Society.
I'm not sure. They do ordinarily they do the Starfest every summer. They haven't done it in the last couple of
I
years.
know there's a group that meets at Westchester University that I've spoken at twice.
That's the Chester County.
Yeah, that's Chester County.
Chesmont does the Starfest.
Yeah. Paul, you've talked to us 2 or 3 times.
Right. So you're right. So that's what I thought.
Yep, they're always great. Yep.
Yeah, thank you.
I always enjoy it.
And remind me, who's the president of the group?
Dave Hockenberry.
Okay. Yeah. How's he doing?
Good. And Roger Taylor before him.
Okay.
Yeah. We had our meeting last Tuesday. It was great. Yeah.
Okay. Yeah, I feel amiss that I'm not going to the groups live, but I guess everybody is virtual.
Well, we had a live meeting on Tuesday, but we also Zoomed it at the same time, which was a little challenging, but we figured it out.
Okay. I am planning to, if possible, go to Lehigh Valley. But that's not until January, and giving a talk there.
Yeah, Zoom and live at the same time is a little tricky.
Yeah, I've done that with my classes.
Yeah.
So, but it's good to see everybody, and I really had fun speaking to the group and some good questions here. And I'd be glad to speak to any other groups in the area. So just let me know. So any other questions?
Thanks very much for coming out. Appreciate it. You're welcome to hang out. When this meeting becomes sort of the virtual, you can probably appreciate this. This becomes a virtual meeting at Manila's Mainline Diner. Only nobody's at Manila's Mainline Diner now.
That will resume, one hopes.
Yeah, we hope that'll happen again soon.
Okay. Well, I think I will say goodbye. And,
thanks very much, Paul.
Thank you. Thanks for inviting me. Thank you.
Bye.
Thanks.
Great talk,
for inviting
Paul.
me. Take care. Thank you. Bye-bye.
And Lewis, I completely skipped you in case you have a report as the treasurer.
My report was that number, 202.
That's what I thought.
Yeah, I mean, in a very general sort of sense, it is September, which means elections are only 3 short months away. So if you think you're putting your hand in the hat, please do. I don't know who's up this year in particular, but everyone is up, right? It's elections. And I'm just flabbergasted that we've popped 200. This is crazy. It is, you could go back 35 years, I think, before you'd have a similar number. There were really large numbers at the very beginning, but it's pretty unprecedented for modern times. And certainly in the 14 years I've been here, 15 years I've been here. Yeah.
I would like to say, if you are interested in being involved, we have unlike probably any other organization I've ever been involved in, folks are really engaged. My job is probably the easiest job in the entire club, and because we have so many people who are actively involved in doing and working. If you're interested in contributing, if you have prospective guests who you think you can get to come to meetings. You have contacts with people who would be interesting speakers. If you're interested in doing outreach, you'll hear from all sorts of people, from libraries, from, as I said, Girl Scout troops today, senior centers. We get a lot of requests for outreach from a lot of different organizations, and Janet Rush does that single-handedly, and I'm sure she could use some help. If you want to help with our newsletter, which is just fantastic, every issue blows me away. Just let us know. Send an email to president@dvaa.org. That's such an easy email to remember. I'm happy to put you in touch with whoever you have to be in touch with.
Yeah.
Love to have you involved, and keep the club going strong. Because
Can
with
I
200,
mention one thing about the newsletters too?
please, Lewis.
We have an archive with maybe one or two exceptions of literally 40 plus years of newsletters online,
Wow.
right? And so it's an amazing resource, not just for the nostalgia buffs, but for people who are looking to get historical astronomical articles. It's crazy. It's I highly recommend it.
That's great. Well, anybody else, anything else for the good of the organization before Jeremy cuts the feed? And you know what? Let me just look at the feed to see if there's any.
No questions there.
No questions. Yep, no questions.
I'm not sure that I can shut it down. All of my controls basically blanked out about halfway through the meeting.
Okay.
Wow.
So we have to commit to half of the cursing that we normally do.
Yeah. Unless you can shut it down.
Let's see. View stream on YouTube. Let's see if I have a way of
I
stopping
can view and copy it. I can't.
It's your account. I can't stop it.
Okay. Yeah, I can't do anything.
Well, why don't you log out and log back in?
All right. You want me to do that?
That's an idea.
All right. So we'll shut everything down and then we'll come back at the end.
Yeah.
Okay.
And if for any reason we're bounced, just come back on.
All right. I think everyone will be bounced.
Okay.
From YouTube or from Zoom?
From Zoom. I think the room will go down.
I don't know if that's true.
I don't think so.
Yeah, right. I host a bunch of meetings that I leave that still continues for other people.
Yeah, it just changes.
Yeah, I can't say for sure because I never do YouTube connected to it.
Well, I'll try to get back in. I'm not sure if I'll be able to.
Okay.
All right.
There's only one way to find out.
Right.
Cross your fingers.
He's blinking his eyes, so he hasn't left.
Even log out.
You can't even log out.
Yeah, it just all the controls blanked out on me. All right.
Wow. What if I made you host?
Let me Alt delete. I'll get out that way.
That modern technology making our lives easy.
A ghost in the machine.
Hey Lou, it came up that you were host or co-host. You were made a co-host. Can you do anything?
No.
I can't add it either.
There we go.
Yeah, and we did not.